In our last video, we had seen how to solve the problems on linear differential equation with constant coefficients when auxiliary equation has real and distinct root. Now let us see how to solve the problems when the auxiliary equation has real and repeated root. Auxiliary equation have real and repeated roots. Suppose the differential equation f dy equal to 0 has n repeated factors. Therefore, its auxiliary equation has n, its auxiliary equation fm equal to 0 has n equal roots. Suppose m1, m2, m3, they all are equal to mn equal to b. Suppose all roots are equal to b. Then we have to find here, we have to find n linearly independent y's. Here we have to find n linearly independent y so that d minus b raised to n y equal to 0. d minus b raised to n y equal to 0. We shall call this as equation second, this as a third, and this is a fourth equation, d minus b raised to n y equal to 0. Then we know the property d minus m raised to n of x raised to k e raised to mx equal to e raised to mx into d raised to n of x raised to k. This property is a well-known property. In this property, if we put m equal to b, what happens? d minus b raised to n of x raised to k into e raised to bx equal to e raised to bx into d raised to n of x raised to k. We will get this. This value, nth derivative of x raised to k, d n of x raised to k is 0 for if k equal to 1, 2, 3 up to n minus 1, then nth derivative is 0. Therefore, d raised to n of x raised to k equal to 0 for k equal to 1, 2, 3 up to n minus 1. And therefore, this value is 0 from this d minus b raised to n of x raised to k b e raised to bx equal to 0 for k equal to 1, 2, 3 up to n minus 1. K equal to 0 also. Up to n minus 1, this is 0. From this equation, nth derivative of x raised to k equal to 0 for k equal to 0, 1, 2, 3 up to n minus 1. And if we put this value here, we will get d minus b raised to n of x raised to k e raised to bx equal to 0 for n equal to 0 up to n minus 1. This is the equation 5. Now, the function yk equal to x raised to k e raised to bx, where k equal to 0, 1 to n minus 1 are linearly independent. Because aside the common factor e raised to bx, they contains powers of x, that is x raised to 0, x raised to 1, x raised to 2 and x raised to n minus 1. Therefore, yk equal to x raised to k e raised to bx is a solution of differential equation 5 for k equal to 0, 1, 2, 3 up to n minus 1. And hence, y equal to C1 y naught, here y naught, C1 x naught e raised to bx plus C2 x e raised to bx plus C3 x square e raised to bx plus Cn x raised to n minus 1 e raised to bx is a solution of the differential equation 5. That means C1 plus C2x plus C3x square plus so on Cn x raised to n minus 1 in the bracket and e raised to b outside of the bracket. This is the solution of the differential equation 5. This number is 6 number. This is a 6 number equation. It is a solution of the differential equation 5. Further, FD contains factor d minus b raised to n. FD has this factor, and therefore FD can be written as, therefore the equation FDY equal to 0 can be written as FDY equal to GD into d minus b raised to n y, where GD contains the factor other than d minus b. D minus b square, d minus b cube and so on, d minus b raised to n. Now, we are able to write solution of differential equation 1, that is f dy equal to 0 for f dy equal to 0 when auxiliary equation has distinct roots. Distinct roots. Not sorry. Auxiliary equation has real roots and a root is repeated n times. Therefore, solution of equation is y equal to c1 plus c2 x plus c3 x square plus cn x raised to n minus 1 e raised to bx, which is linearly independent solution. On this part, theoretical question may be asked: obtain the general solution of the linear differential equation with constant coefficients when auxiliary equations have n repeated roots. In this way, question can be asked. Or show that y equal to c1 plus c2x plus c3x square plus cn x raised to n minus 1 into e raised to bx is a repeated root, is a solution of the linear differential equation f dy equal to 0 when auxiliary equation has n repeated roots. In this way, question may be asked on this part. Now, we shall solve some problems on this method. We have to solve the problem. Solve d raised to 4 minus 3d cube minus 6d square plus 28d minus 24 y equal to 0. For this, we shall write first auxiliary equation. Auxiliary equation is m raised to 4 minus 3m cube minus 6m square plus 28m minus 24 equal to 0. We have to find out roots of this equation. For that purpose, we shall add all the coefficients. They are not 0. Therefore, m equal to 1 is not root of this equation. Now, we shall add coefficients of even power of m, that is 1 minus 6 minus 24, that is minus 29, and coefficients of odd terms minus 3 plus 28, that is 25. They are not equal. Hence, m equal to minus 1 is also not root. Now, we shall check whether 2 is a root. For that purpose, we shall put m equal to 2 in this equation. 2 raised to 4 is a 16 minus 2 cube 8, 8 into 3 24, 2 square 4, 4 into 6 24, 28 into 56 minus 24. See, 24, 24, 24, 72, and 56 and 16, 72, 72 minus 72 equal to 0. Therefore, m equal to 2 satisfies this equation, and hence m equal to 2 is the first root. For finding other roots, we shall use synthetic division method. We shall divide by m minus 2, that is 2 is here, and we shall write the coefficient in decreasing order: 1, minus 3, minus 6, 28, minus 24. 1 is carried forward as it is. 1 into 2 is a 2, minus 3 and 2 is a 1, 1 into 2 is again 2, 2 and minus 6 is minus 4, minus 4 into 2 is 8, something went wrong. 1 into 2, minus 3 and 2 is a minus 1, minus 1 into 2 is a minus 2, minus 2 and minus 6 minus 8, minus 8 into 2 minus 16, therefore there is 12, 12 into 2 24, this becomes 0. Now again we shall take 2, we shall see whether this becomes 0 or not. 1, 1 into 2, 2, 2 and minus 1 is 1, 1 into 2, 2, 2 and minus 8 is minus 6, minus 6 into 2, minus 12, therefore 0. Therefore, the 2 is 2 times root of this equation. Now, this polynomial can be written as m raised to 4 minus 3m cube minus 6m square plus 28m minus 24. This can be written as m minus 2 2 times into m square plus m minus 6, m minus 2 bracket square into m square plus m plus minus 6. 6 has the factors 3 into 2, so that 3 and minus 2 equal to 1. Therefore, we can write this as m, okay, 3 into 2. It can be added minus 3 and minus 2. Therefore, the factors of m square plus m minus 6 are m plus 3 and m minus 2. Thus, roots of this auxiliary equation are, this must be equal to 0, and therefore roots of the auxiliary equation are m equal to 2, 2, 2 and minus 3. Therefore, general solution is y equal to c1 plus c2x plus c3x square into e raised to 2x, as 2 is repeated 3 times, plus c4 into e raised to minus 3x. Minus 3 is only one factor, it is not repeated. Therefore, solution is c1 plus c2x plus c3x square in bracket into e raised to 2x plus c4 into e raised to minus 3x. We have to solve the problem d cube plus 3d square plus 3d plus 1y equal to 0. Its auxiliary equation is m cube plus 3m square plus 3m plus 1 equal to 0. Clearly, this is m plus 1 cube, and hence m equal to minus 1, minus 1, minus 1. And therefore, general solution is y equal to c1 plus c2x plus c3x square into e raised to minus x. As minus 1 is repeated 3 times, we have to take 3 constants c1, c2, c3. Our problem is solve d cube plus 6d square plus 12d plus 8y equal to 0. Its auxiliary equation is m cube plus 6m square plus 12m plus 8 equal to 0. Clearly, this is m plus 2 bracket cube. See, expand this, m cube plus 3 into 2 times m square plus 3 into 2 square times m, 3 into 4m, that is 12m, plus 2 cube 8. Therefore, this is perfect cube of m plus 2, and therefore m equal to minus 2, minus 2, minus 2. Therefore, general solution is y equal to c1 plus c2x plus c3x square into e raised to minus 2x.